Hi, welcome. Today my topic is about the compressibility factor. So, in the gaseous state, we had discussed already discussed about the ideal gas equation and its derivation, kinetic model of the gas, and today I am going to discuss about the compressibility factor. So, I hope every one of you must be knowing about the PV is equal to nRT, or this can be also written as PV MRT. This is Vm means molar volume. That is volume of the gas, one mole of the volume of the gas when you have taken 1 mole of the gas. Okay. So, now the compressibility factor is defined as the PVM by RT. Okay, this is compressibility factor. So, it gives the information about the ideal or non-ideal behavior of the gas. If compressibility factor means compressibility factor Z is equal to 1 means it is PV is equal to nRT, that is PV is equal to nRT, that is the ideal equation. When you divide PV by nRT means Z is equal to 1, compressibility factor 1 means this is ideal. Okay. Now, there are two conditions, Z can be greater than 1 or Z can be less than 1. So, these two conditions we say that it is non-ideal behavior. Okay. So, compressibility factor gives the information about the ideal and non-ideal behavior of the gas. Okay. So, Z is equal to 1, ideal, Z is less than or greater than 1 means non-ideal behavior. Okay. Now, so we can we can discuss more about the compressibility factor. So, if a plot is Z versus a plot Z versus pressure, compressibility factor versus pressure. Okay. So, in an ideal condition, what should be its value, or if a gas is obeying ideal gas, so the Z is always 1, that is Z versus pressure will be always 1, right. So, you can say that this is for Z is equal to 1 and a ideal. Okay. Z is equal to 1. So, Z is less than 1 in this direction and here it is greater than 1. So, ideal condition I have so you can say that ideal condition this should be, if the gas is obeying the ideal gas equation, you can say that the plot versus Z versus pressure will be a parallel or a straight line. Okay, it is always 1. So, but there are the when Z is 2, (600) etc. What is found So, this is an experimental observation, and here in the x axis we have the increased pressure 200 atm, 400 atm, 600 atm and 800 atm, and in the y axis the compressibility. So, I told you the below this line, this is actually 1, this is 1, okay, and here it is 1, and here it is less than 1, and here it is greater than 1. Okay. So, compressibility factor for the very this is 200, 400 and 800 atm. Okay. So, what happened, you can say that at very high pressure, 200 atm means very high pressure actually. So, in low pressure, you can say that in the very low pressure, all gases obeying the Z is close to 1. That is, all gases, ammonia, carbon monoxide, H2CH, etc., all gases having Z is equal to very close to 1 at very low pressure. When pressure increases, okay, when pressure increases, Z value changes, compressibility factor changes. So, here H2 and helium, they have always Z is always greater than 1 at very high pressure, Z is greater than 1. There is no value in the less than 1. You find here, this curve is not going below the Z is 1. So, you can say that overall 3 behavior has been observed. First one, at low pressure, all gases having Z is very close to 1, because this graph start from 1. Okay, that is why all gases obeying Z close to 1. But when the pressure increases, some gases are showing always a Z is positive or greater than 1, sorry, positive not, is greater than 1, and for example, in the case of carbon monoxide, at appreciable of 200 to 400 atm, so it value is less than 1, but after that it is greater than 1. Okay. Similarly, for NH3 also it has the less than 1, and later it is greater than 1, and similarly NH3 gas has the very less than 1. Okay. And as the pressure increases, it also become greater than 1. One more important things you have to note down here, it is that all gases having the greater than 1 at very high pressure. When pressure is increased very high, 400 atm, greater than 400 atm condition, you find that all gases having Z is greater than 1. Why? Okay. So, let us discuss that things. Okay. So, you can summarize one, extremely low pressure one first thing is this is plotted at 0 degree centigrade. Okay. So, this is temperature is kept constant at 0 degree. These all graph having these Z is temperature kept constant 0 degree. Okay. At low pressure, all gas have all gases have Z is close to 1. Okay. Second observation, at high pressure, at very high pressure, sir, all gases have Z is greater than 1. Okay. Z is greater than 1. And third point, means what does it mean? All gases Z is greater than 1 means they all are means they are incompressible than ideal. Okay, that is, which means indicate that gases are less compressible than the ideal gas. Ideal. Okay. This is due to when very high pressure is applied, the internuclear repulsion will start. Okay. So, you can say that when pressure is appreciable pressure, why these Z is less than 1, they are means they are compressible and they can be converted into liquid or like that, or that is there is an intermolecular force of attraction start. Z is less than 1 means when less than greater than 1 means the gas are the internuclear repulsion will start. Okay, internuclear repulsion will start. When you compress further, what will happen? They will internuclear positive repulsion will start. That is why when all gases when apply very high pressure, you can say that in that condition the Z will be greater than 1. Okay, they are compressible than they are compressible, less compressible than ideal gas. This is due to high pressure. Internuclear. This is due to at high pressure internuclear repulsion start. Okay. So, this is about the when Z is greater than 1. Now, Z is less than 1. Okay. So, I told you this is because of the internuclear repulsion start at Z is greater than 1. Now, Z is less than 1, it is due to, you can say that it shows moderately high pressure. Okay. So, you can say that at Z is less than 1 for COCH4NH3 at a moderately low pressure, and in that condition intermolecular attraction is dominated. Okay. So, Z is less than 1, Z is less than 1, here intermolecular attraction dominate. Okay. Example, the COCH4 NH3 at below 400 atm pressure. Okay. So, this is all about the compressibility factor. So, you just remember this plot, okay, compressibility versus pressure, and also you remember the 3 conditions I have discussed. This is about compressibility factor. Effect of temperature. Effect of temperature on deviation from ideal behavior. Okay, that is Boyles temperature. Effect of temperature on Boyles temperature. So, again let me draw a graph, Z versus temperature. You also keep on drawing. So, what is the So, here again we have taken Z versus pressure, compressibility factor versus the pressure, and each time we have changed the temperature and how the compressibility factor is variation of compressibility factor. So, what you found for nitrogen gas, we have taken nitrogen gas and you found that this is actually Z is equal to 1, this is Z is equal to 1. Z is equal to 1 in an appreciable range of pressure for 50 degree. When the temperature is goes on decreasing, it is again further at a lower pressure range, and the temperature is 20 degree, and at a lower pressure and temperature 20 degree, Z is less than 1, and again Z is minus 25 degree when at initial Z is less than 1 and later Z is greater than 1, like that. So, here this above region Z is greater than 1. So, what you observe from here, from the graph, you can not keep on note down the things like so we have drawn what is the graph. It is the effect of temperature on compressibility factor. Compressibility factor at different temperature, that is 50 degree, 20 degree, minus 25 degree and minus 70 degree. Okay. So, from the graph it is clear that compressibility factor is unity, Z is unity for Z is unity for 50 degree, when the temperature is 50 degree up to 200 atm. So, when temperature so in this region you can say that this 50 degree plot is unity, 50 degree plot is Z is unity above up to 200, after that Z is greater than 1. Okay. So, so that is PV is remain constant, PV is remain constant. Okay. That is high that is obey the Boyles law, that is it obey the Boyles law, that is in another words it obey Boyles law, right, it obey Boyles law. But this minus 20 degree, minus 25 degree and minus 70 degree do not obey even in this temperature. Okay. So, that is Boyles law is obeying, in an appreciable change of pressure at 50 degree. That is what I have written here, that is Boyles law is PV is constant is Boyles law. Boyles law is obeying at appreciable range of pressure. appreciable range of pressure. Okay, so that is why this temperature is called the Boyles temperature. How you define the Boyles temperature? You can define the Boyles temperature above particular temperature, above particular temperature, gas is obeying Boyle's law. Boyle's law within the appreciable range of pressure is called Boyle's temperature. Gas is obeying the appreciable range of pressure is called Boyle's temperature. So, Boyle's temperature. So, again I told you here from this plot we found that Boyle's temperature for nitrogen gas is 50 because it obeys the Boyle's law within the appreciable range of pressure. So, this the Boyle's temperature for nitrogen. So, similarly you can also note down the Boyle's temperature for different gas, like gas Boyle's temperature. Okay, hydrogen into, that is for helium it is minus 240 degrees centigrade, for minus 165 degrees. That is above this 50 degree nitrogen gas will always obey the Boyle's temperature, Boyle's law, okay, in appreciable range of the pressure. So, you can say that these are the Boyle's temperature for different gas. That is, for nitrogen it is 50 degree, hydrogen it is minus 165 degrees. My question is in the 50 degrees centigrade temperature, whether hydrogen gas obey Boyle's law within the range of appreciable range of pressure? You find your answer. Okay, so this is all about the Boyle's temperature or effect of temperature on deviation from ideal gas. I will continue in the next class. Do your assignment. Thank you for watching.